The next part of our lesson talks about the pH scale and the pH concept, and how does the hydrogen ion and hydroxide ion, that information in terms of their molar units, help us to determine the pH of an acid or a base. So in the pH concept, here's what we have out for tools. I have my notepad opened. It's on page 7. I will need a calculator and of course something to write with. When ready, let's start that lesson. The pH concept, about quarter of the way down on page 7. It says since the hydrogen ion concentration in moles per liter is inconvenient to use, a more widely used system called the pH scale is used. The pH scale is just a numbering system used to measure the acidity or alkalinity of a solution. It's a numbering system that allows us to determine how acidic or how basic a solution is. What we're saying is these values that we were looking at up above, let's just say the numbers that we had written together in our previous lesson, notice how they are very, very tiny numbers, lots of decimal places. We're saying that those moles per liter, big M molar units, are inconvenient. We're going to create a numbering system that goes from 0 to 14, and just based on the number, it's going to tell us how acidic or how basic a solution is. So the pH scale is simply a numbering system. It's a measure of how acidic or basic a solution might be. It's a numbering system from 0 to 14. Let's take a look at a pH scale, and I'm just going to put a picture from our own chemistry book up on the screen, and we'll start to examine the scale. This is a picture right from our chemistry book. It's found on page 584, and I want us to examine what we see. Let me bring that in close up so we can get a good look at it. Notice we've got some things going on. As I go high or low, we're increasing acidity or decreasing acidity or increasing basicity. We have the opposite ends of the spectrum as we climb away from the center of our pH scale. We have a column that's giving us the concentration of hydrogen ion in molar units. We have the concentration of the base ions called hydroxide in molar units, and how they relate to a numbering scale from 0 to 14 on a pH scale. We have some examples provided for us as well, an aqueous system such as hydrochloric acid, gastric juice, lemon juice, tomato juice, my favorite, black coffee. We see some examples of milk, pure water with 7.0, baking soda called sodium hydrogen carbonate, milk of magnesia. We talked about that as milk of magnesia neutralizes our excess stomach acid if we have an upset stomach, household ammonia, sodium hydroxide. Some of these were samples that we tested in our lab just to determine if ordinary household ingredients were common acids or bases. What we'd like to do is to sketch in a pH scale into our note packs. When I ask you to sketch in the pH scale, perhaps you'd like to pause this video and take your time to carefully draw in this particular diagram. What I'd like to see in your note pack is how the relationship of H plus times OH minus always gives us that value called Kw, 1 times 10 to the negative 14th. Make that observation that when you look at the power on the exponent, they're always giving me the power of 14, the constant called Kw. Recalling from our previous lesson, that ion product constant for water is found when we multiply the concentration of the acid ion times the base ion, and that constant we called 1 times 10 to the negative 14th. As you create this picture, this diagram in your notepad, you will notice every time you write an exponent for one ion, the other ion's concentration will give you that power of 14. The other observation, I'd like you to have a moment of aha as you begin creating this sketch in your note packs. Look at the power on the hydrogen ion. When the hydrogen ion exponent is raised to the 0 power, the pH is 0. When the exponent on the hydrogen ion is -1, the pH is 1. When the exponent on the hydrogen ion is -2, the pH is exactly 2. That pattern you'll notice on the hydrogen ion, 0 to 14, always matches the pH of our solution. Pause the video and please take your time to draw this particular diagram in very carefully. I want to see this picture exactly as it appears because drawing it will help to increase your learning. As you create this diagram, you can't help but notice the pH scale directly correlating to the ion concentration of hydrogen, and that the product of H plus and OH minus is always 14. I'd also like you to put in some examples as you see them here. Pause the video, get this copied into your notes, and when ready, start it up again. When you started your video back, I now know that you've got a great copy of your pH scale, best you can, fitting in some area here. You've made a great observation about pH and how it corresponds to the concentration of the hydrogen ion, looking at the power of the exponent from the base 10. Well, what that actually ends up to be is a logarithmic function. Logs on our calculator are the base power of 10. When we put a negative sign in front of the log, that's to turn that negative exponent into a positive integer. If we know the concentration of the hydrogen ion, we can simply find the pH as a look at the base 10 and that power of the exponent. For instance, a moment ago when you wrote down the concentration of a hydrogen ion being 1 times 10 to the -1, you corresponded that to a pH of 1. And you made that observation because the power on the exponent was 1. Now watch on your calculator. If you hit negative log 1e -1, 1 times 10 to the -1, just as we're showing on our paper here, and equal, it's 1.00. The negative log of the hydrogen ion is indeed the pH of our solution. It's that easy. It's turning these decimals, like this would be 0.1, into a numbering system from 0 to 14. The power of the hydrogen ion, our pH scale. If we know the concentration of hydrogen ion, we can hit negative log concentration of H plus, and we can turn our decimal, the molarity unit in a decimal, into an integer between 0 to 14. Give us an idea of how acidic or how basic our solution is. For pH calculation, concentration should be expressed in exponential form. For example, 0.01 molar. If the concentration of hydrogen ion is given to us as 0.1 molar, you might recognize that to be 1 times 10 to the -2. It's the same number, just written in one written decimal form, the other written in scientific notation. But now I can clearly see that exponent would give us the pH of 2.00, a whole number when we have 1 times 10 to those. No worries, if you hit negative log 0.01, indeed your calculator says 2. The pH of our solution is 2.00. Now I'm going to stress something. Whenever we report pHs, they should always have 2 decimal places. That's a chemist's rule of thumb. Even if it's a whole number, we're going to report 2 decimal places. pH of 2.00 is the pH of a solution that has a hydrogen concentration of 0.01 molar. Suppose we have a hydrogen ion concentration, that's H+, equal to 1 times 10 to the negative 10th moles per liter. That's another way of writing big M, molarity. What's the pH of our solution? And again, if I have 1 as the base, 1 times 10 to the, I can simply look at the power here and recognize the pH of our solution to be 10.00. Prove it to yourself. Negative log of 1 times 10 to the negative 10th power is indeed 10. The power of tens. On a logarithmic scale, it's by a factor of 10. Now let me stress that, and I'm just going to sketch what you did very nicely. Let's suppose in my sketching I have a pH scale, or better yet, let me be better than that. Let me put that pH scale back up on this, and that one matches yours, and we can have a common ground to look at. Let's suppose I have, well, let's just look at gastric juice, and let's say that's 2.00, and lemon juice, I know that that's not, it's kind of between 2 and 3, but my point is I want to find examples where I have a factor of difference of 1 on the pH meter. Let's just say that gastric juice is 2.0 and lemon juice is 3.0, just to have a common ground to look at. I know it's not pointing directly at that, but let's just pretend it is, because my point is, even though I've just moved one number on the number line, it changed by a factor of 10. That gastric juice is 10 times more acidic than lemon juice. Look at pure water, 7.0. Black coffee is 5.00. Even though that's just 2 numbers away on the pH, keep in mind it's factors of 10. So it's 10 times 10. It's 100 times more acidic. Black coffee, 100 times the acidity of pure water. We'll get an idea every time we move on our number line. It's by a power of 10, the factors of the logarithmic scale. So the number line is simply showing us the power of 10 that we have our hydrogen ion. And every time we have a hydrogen ion given to us, the negative log of that value gives us the pH of our solution. For example, if we see a hydrogen ion with a molarity unit of 1 times 10 to the negative 4, look at the power on the 10. As long as it's a 1 times 10 to the something, I simply look at that exponent, and indeed the pH is 4. But friends, remember, 2 decimal places is our rule of thumb, 4.00. Letter B, 0.0001 molar. 0.0001 molar, written in scientific notation, you might recognize that to be the same as the number above. The decimal form or the scientific notation form still arrives at the same answer for our pH unit. Letter B is also 4.00. These both lie in the pH range of acids. In letter C, negative log, let me count those zeros with you. 1, 2, 3, 4, 5, 6. 6 zeros and then a 1. 1, 2, 3, 4, 5, 6 zeros and then a 1. Well, that's a same as writing 1 times 10 to the negative 7th. So again, letter C and letter D are the same number, just expressed in a decimal form or the scientific notation form. pH is a numbering system telling us how acidic or how basic our solution is, and it's found by knowing the concentration of the acid ion. Logarithmic scales are on a base power of tens. Sliding on the decimal line of the pH scale is by a power of 10. Suppose we know the pH of a solution. How could we work backwards with our formula to find the hydrogen ion concentration? If our pH is given to us as 6.0, 6.00 would be a better way to type that, 2 decimal places, that becomes the power on the times 10 to the. So in other words, if I were to rearrange the same equation here, rearranged, that the hydrogen ion is found by calculating base power of 10 raised to the negative pH. Base power 10, negative pH. Base power of 10, negative pH. And notice what we'll get? I just do this. 10 raised to the is my caret key, negative 6, and you get a number. 1 times 10 to the negative 6th power. That becomes the exponent, and that would be a molarity unit. The hydrogen ion concentration, 10 raised to the negative pH. So again, here's a series of whole numbers. 10 raised to the negative pH of 5 is 1 times 10 to the negative 5th. And that's a molar unit. pH of 7, 10 raised to the negative pH, 1 times 10 to the negative 7th. You'll see a pattern. 10 raised to the negative pH of 6, 1 times 10 to the negative 6th. Big M for molar units, the power on the hydrogen, pH. 10 raised to the negative pH unit of 3.001 molar. Or, since my calculator put it in decimal form, yours might have done 1 times 10 to the negative 3. These can be written either in decimal form or in scientific notation form, your choice. Now, everything we've done so far has come from a whole number where the decimals have been 0.00s, or the base powers always come from a factor of 1 times 10 to the, but that's not always the case. Sometimes pH values are not whole numbers. It doesn't change a bit of the math. They're still easy enough to find using our formula for pH. Just to remind ourselves, pH is hit by finding negative log of the hydrogen ion. Also remember, chemists often use hydrogen ion interchangeably with the hydronium ion, H3O plus 1. These both represent the acid concentration, so either negative log H plus or negative log H3O plus, same thing in my mind. Now, remember, we had a relationship between the acid ion, hydrogen, and the base ion, hydroxide. We can derive another powerful formula for calculating the power of the base ion, hydroxide. That POH can be found by hitting negative log of hydroxide ion. Let me make sense of that with this returned visual. When I looked at the hydrogen ion concentration, we found a pH unit. pH comes directly from hydrogen. POH came directly from the base ion, hydroxide. When the pH is 0, POH is 14. When the pH is 1, POH is 13. pH is 2, POH is 12. We see the relationship between pH, power of hydrogen, and POH, the power of hydroxide. The POH is negative log of hydroxide. If pH is found by knowing negative log of acid ion, and POH is found negative log of hydrogen hydroxide here for the POH, we see that they always come up to be the ion product constants 14. pH plus POH is always 14, the top of our pH scale. When the exponent on pH and the exponent on POH, notice that they always gave us the power of Kw, the ion product constant of 14. So that's just our aha moment that these exponents top out at 14. pH and pOH summed will top out at 14. What's the pH of a solution if we know hydroxide to be 4 times 10 to the negative 11th power? Well, this is hydroxide. So if I were to hit negative log of the given value, 4 times 10 to the negative 11th, I'm going to get something called pOH. Let's hit that so far. Negative log of 4 times 10 to the negative 11th. pOH is 10, and we need 2 decimals, so 397. Let's make that 10.40. But it didn't ask for that, did it? It asked for pH, and right now I'm at pOH. It's an easy flip. 14 minus 10.40 is our pH. 14 minus 10.40, and we have a pH of 3.60. We were given hydroxide. When you negative log hydroxide, you get something called pOH. 14 minus the pOH flips it very easily into our measuring tool called the pH scale. 14 minus 10.4 gave us an acid range, 3.60. This is some calculator work, and I really don't necessarily need to see this all on your paper. It can be as easy as 14 minus, if it's hydroxide, to flip it to pH. Hydrogen ions directly give me pH, but hydroxide ions get me pOH. So I just remember that if I'm doing hydroxides, there's that last additional step to flip pH out of pOH. Let's model what that means. Letter A, B, and C want me to calculate pH. pH, H, pH, they go directly together. I'm just going to negative log. Letter A, hit with me. Negative log 5.0 times 10 to the negative 6. 5.30, the pH of our solution. Negative log 8.3 times 10 to the negative 10th. pH 9.08. Letter C, again a direct measure of hydrogen, so negative log 2.7 times 10 to the negative 7th. pH 6.57 pH units. Now notice D, E, and F, a little bit different, aren't they? They're giving us the base concentration. When I negative log this value, we get something called pOH. So, negative log of 4.3 times 10 to the negative 5th, my pOH, 4.37, don't quit, 14 minus that, there's my pH, 9.63 pH units. See that extra step? 14 minus pOH. If I'm measuring pH, but I'm given hydroxide, it's a little extra step, 14 minus the value. Let's do letter E together. Negative log 2.0 times 10 to the negative 5th. When I negative log a hydroxide, this number is my value of pOH. 14 minus that answer, and here's my pH, 9.30 pH units. And one more, negative log 4.5, E negative 11, and that's pOH, hydroxide's power. 14 minus conveniently flips that to a pH of 3.65 pH units. Let's go back and remind ourselves. Letter A, a pH 5.30, that's in an acid range. Letter B, a pH of 9.08, that's in a base range. Letter C looks slightly acidic, very close to 7, still not exactly 7, so we can't call it neutral. It's slightly acidic. D and E, both with pHs in the 9 range, are bases. And letter F, a number well below 7, very acidic. It's a numbering system that gives us insight into how acidic or how basic our solution is. Negative log of pH, negative log of pOH, together their sum is always 14. On our next example, let's just record so it's on both papers here. Here's what we know. pH is negative log of hydrogen ion. And if I turn that around, 10 raised to the negative pH gives me hydrogen. Let's do the same thing for pOH. pOH is negative log of hydroxide ion. So 10 raised to the negative pOH gives me hydroxide's value. And together we know pH plus pOH gives us 14. So just some useful, useful formulas as we try to manipulate one into the other. So if I had any one of those 4 formulas, I could easily find the other values. What's the hydrogen ion concentration in molarity units for a solution with a pH of 3.7? What's the hydrogen ion concentration? I know the pH. The hydrogen ion concentration can be found by hitting 10 raised to the negative pH value. Hit on your calculator. What's 10 raised to the negative 3.7 power? 10 raised to the negative 3.7, 1.995 times 10 to the negative 4th molar units. You want to say that's 2.0? We can round a little bit. 2.0 times 10 to the negative 4th molar units. 10 raised to the negative pH. We're going to do that as a series here. 10 raised to the negative pH, finding hydrogen ion. Notice it's a direct match, just a one-step. pH comes directly from H+. I don't see any mismatch with hydroxides in there. So 10 raised to the negative 7.3. Our molar concentration of hydrogen, 5.01 times 10 to the negative 8th molar units. 10 raised to the negative 1.8. 0.016 molar units. 10 raised to the negative 9.5. 3.16 times 10 to the negative 10th molar units. 10 raised to the negative 6.7. Here's one again we'll round. 2.0 times 10 to the negative 7th molar units. Each and every time we had a pH, we could very easily turn that back into the concentration of the acid ion hydrogen. Using our values from the above, let's turn this into the concentration of hydroxide ion. And friends, we actually have some choices here. Here's what we know. Kw is a constant. Using my answers from above and the constant called Kw, just as in the previous lesson, we could take 1 times 10 to the negative 14th and divide out, factor out the hydrogen and turn it to hydroxide. But a few less strokes on the calculator, less keystrokes, there's an easier way, I think, to do that. If I know the pH, but I want to know hydroxide, I'm going to do this formula, 10 raised to the negative pOH, and that gives me hydroxide. It's just fewer keystrokes. Let me model that. Remember here, letter A had pH of 7.3, 10 raised to the negative 7.3 is where I got hydrogen. But what if we go like this? 10 raised to the negative 14 minus pH, and see in my parentheses, that's the very definition of POH, isn't it? So on my calculator, I think it's easier than hitting all those times 10 to this. I'm going to go 10 raised to the, see that caret key there? Then I'm going to go negative, parenthesis, 14 minus the pH value of 7.3. And that's the concentration of hydroxide. So in letter A, 2.0 times 10 to the negative 7th molar units, the concentration of hydroxide. And I bet if we were to multiply these together, the concentration of H plus and the concentration of OH minus, we're going to get the Kw constant 1 times 10 to the negative 14th. And let's just show ourselves that relationship. Pretty darn close. 1 times 10 to the negative 14th. If I just round that, it's 0.111 repeating. So very, very close, and I suppose it's just due to the rounding of up above. So we have indeed shown ourselves either way could get us to the same story. 10 raised to the negative POH is fewer keystrokes. So if I were to model letter B, using my pH of 1.8, I go like this, 10 raised to the negative, then a parenthesis, 14 minus pH, and in my parenthesis, I'm letting that stand for POH. My hydroxide, 6.31 times 10 to the negative 13th molar units. Do the next one with me. 10 raised to the negative POH. To turn pH into POH, I do the 14 minus trick. 14 minus the pH of 9.5. Hit enter. Our hydroxide, 3.16 times 10 to the negative 5th molar units. I just noticed that. Letter D. Letter D. 10 raised to the negative, and then in a parenthesis, let's flip the pH into POH by doing the 14 minus trick. 14 minus 6.7. And our hydroxide is 5.01 times 10 to the negative 8th molar units. Here's some things that we've learned today. The pH scale. pH scale is a numbering system, all based on the power of tens. The power of 10 on hydrogen ion, the acid ion. The lower the number, the more acidic the solution. The higher the number, the more basic the solution, with 7.00 being exactly neutral. I've also learned that when I multiply H plus times OH negative, it is indeed a constant. When I look at those multiplied values, every time it comes out to be 1 times 10 to the negative 14th. Looking at those tiny little decimal numbers, chemists have devised a convenient scale to turn tiny little decimals into numbers that lie between 0 to 14 by using a logarithmic scale, the power of 10. Sliding just a little bit on the pH scale are actually huge swings in the pH range. pH of 13, pH of 14, that's a difference by a power of 10. pH of 12 compared to 14, that's 2 spots away, 2 zeros, it's 100 times more basic, and so forth. Powers of 10 is the magic of a logarithmic scale. We've also learned the relationship between pH and POH. Together, pH and POH always add to 14. We find pH if we know the acid ion concentration. We find POH if we find the base ion concentration and can easily convert one unit into the other, knowing that they always add to 14. At this time, you're done with your video lesson on Moodle, and you are ready to begin your worksheet on calculating pHs.